During a drone competition, my science club team and I flew an electric aircraft over a simulated chemical contaminated airport. The mission was to release light beacons to mark the danger zone for firefighters. We had to plan 2 flights. Halfway through, we replaced the battery. Not because of a failure, but because we knew the power wouldn't last long for the whole mission. That moment made me realize how crucial energy optimization is in UAV operations. How can we make electric UAVs fly longer using the same battery power? Electric UAVs, especially helicopters, have a serious limitation: endurance. The more they spend time climbing, hovering, changing direction, the more energy they consume. Once the battery drains, the mission ends, whether the job is done or not. So the challenge isn't just battery size. It is how efficiently the UAV uses energy during flight. My research focuses on optimizing the energy consumption of an electric-powered unmanned helicopter. To do that, I analyzed 2 main factors: the rotor speed and flight path. I studied how they interact to influence the energy use. Instead of keeping constant the rotor speed, I designed a control model that adjusts the rotor speed dynamically depending on whether the helicopter is cruising or landing. And at the same time, I developed a smoother path that avoids unnecessary climbs and sharp turns. In simple terms, the helicopter learns when to speed up, when to slow down, move smarter, not harder.
I like very much this flight path optimization, but my question is, if you make this comparison, to make the comparison for some of the case studies, some of the scenario, how you did this. When we should consider a different scenario of the flights. Yeah. And the question, how you select this for the comparison. In one case can be 1%, in another can be maybe 25%. And probably you select some of the case. So how you did it?
Yeah, so some literature, some papers do focus either on the rotor speed or flight path. I decided to combine these 2 strategies together because of their interaction effect that help to reduce overconsumption during climbs and hover. I adjusted the rotor speed and the flight path parameters, and combining these 2 strategies helped to achieve this 20% energy savings.
Thank you.
To clear it up, it was tested in real-life scenarios, not just in simulations, in simulated conditions, but in real life. So
I'm involved in competitions, and based on the experiences that we have obtained, I had to focus on analyzing the rotor speed and flight path interaction. So this is strictly simulation-based.